Today we will be seeing various distributed energy resources like small scale hydroelectric power generations, some storage devices, etc. So first let's start with small scale hydroelectric power generation. Hydroelectric power is nothing but the generation of power from the movement of water. A hydroelectric facility requires a dependable flow of water and a reasonable height for the water to flow, called a HUD. In a typical installation, water is fed from reservoir to a pipe into a turbine. The water flowing to the turbine causes an electrical generator to rotate, converting the motion into electrical energy. A small-scale hydroelectric generators are usually employed to generate power effectively on-site in microgrids. And the amount of power generated depends on the annual rainfall and topography of an area. The output of these generators undergoes large variations due to variable water flow caused by uneven rainfall. This is mostly true for hydropower stations with catchment area spread over rocky soil without vegetation cover and which do not have their own storage reservoirs. Variable water resources also lead to varying generation with a low capacity factor, and the ratio of available energy to its rated annual capacity is defined as the capacity factor. And so this is the equation for the power output of a small scale hydroelectric power generation. P is given by QH eta rho G, where P is the power output, H is the effective head, eta is the overall efficiency, rho stands for water density, and G stands for acceleration due to gravity. So here rho and G can't be changed, so power output mainly depends on water flow rate and effective head. So as indicated in the equation, by increasing both water flow rate and effective head, the power output can be increased. And here the water is brought to the turbine through a pipeline called penstock, and that cross section of that penstock is designed suitably for optimum water flow. So different types of water turbines are employed depending on available flow rates and water heads. Generally, inbuilt turbines like turbo turbines, Belton wheels, they do operate at higher heads, and reaction turbines like Kaplan, Francis, etc., they do operate at lower heads. And in inbuilt turbine, power is extracted from kinetic energy of water jets at atmospheric pressure, while reaction turbines, they do extract power from pressure drop. Cross-flow inverse turbines are also employed for small hydro units where kinetic energy is extracted from water striking the turbine blades as a water sheet rather than a jet. With suitable multiple ratio gearboxes, both induction and synchronous generator can be used for small-scale hydropower generation. Although appropriate precautions must be taken while designing the turbine to avoid damage that may occur due to overspeeding during sudden loss of flow. Coming to other renewable energy sources, biomass, municipal waste, landfill gas, etc., they are considered as other renewable distributed energy resources for electricity generation. And the location of the generators is chosen based on the availability of the resources. Foremost drawbacks of these resources are low energy density, scarcity of resource, and difficulty in storing them in huge quantities. As storage is not cost effective, these generators are usually of small capacity and they do operate close to the resources as load pockets. So coming to storage devices, energy storage is important for utility, SPU systems, for uninterrupted power supply, and energy systems in remote areas. Energy storage has been always related closely with solar installation, including solar heating and solar power systems. And the storage options, they are necessary when unpredictable sources are used in standalone and islanding power systems. The backup energy storage devices must be incorporated in microgrids to guarantee continuous power supply. They are storage batteries, flywheels, and ultra capacitors. And these devices should be connected to the DC bus of the microgrid and provided with write-through capabilities during system changes. So with increased deployment of renewable distributed energy resources, Energy storage will grow in importance mainly due to the following two reasons. The first one, most of the distributed energy resources are discontinuous and they do generate power when the atmospheric conditions are favorable rather than when energy demand is there. Second one, energy must be carried in the vehicle for transportation systems. So based on the following parameters, the storage technology is selected properly. They are unit size of the storage device is chosen based on the applications. For example, large units support grid connected renewable distributed energy resources technologies. Then comes storage capacity. Storage capacity is nothing but it's the total energy available after complete charging. And then comes available capacity. It's the average value of output power based on the depth of discharge. Then comes efficiency. Efficiency is nothing but it's a ratio of output energy from the storage device to the input energy of conversion technology to storage device. Then comes cost. Cost here, installation, operation and maintenance cost of storage device throughout its lifespan come under cost. And feasibility, that's a degree of flexibility to storage applications, and continuity of the service is the reliability. So these are the storage technologies has to be selected based on these following parameters. So applications of storage devices in electrical power systems is summarized below. First one, time shift in electric energy. So during off-peak hours when prices are on low side, energy is purchased, and when the price is higher, it can be sold. The energy which is stored can be also used to avoid expensive purchase during hours of high demand. Then comes wear, control and power factor correction. Polytronic interfaces actually present the capability to vary the reactive as well as the real power rapidly. Load following. In order to keep the stability of utility grid, the storage device responds to the demand of the consumer. Actually, the storage device is either discharged or charged to meet the requirement of the utility grid. Then load leveling, it's nothing but during light load periods, the storage units are charged using low cost energy from base load plants, and during high load times they discharge when the energy value is higher. Then comes spinning reserve. Because of the capability to increase the output quickly, these storage devices with polytronic interfaces can act as spinning reserve, reducing the requirement for conventional spinning reserve units. Black start capability. Stored energy can also be used to start an isolated generating unit. And bulk energy management. So actually bulk power transfers can be postponed by storing the energy unit it is required or until its value increases. Then reliability in service. So inclusion of storage devices helps to improve the reliability of power supply. So in case of long-term power outage, the storage devices provide sufficient energy backup to carry out either safe shutdown of weak equipment or right through the entire outage. Power quality improvement. The energy storage device also employed to offer power quality services to the consumers, and it can be used to maintain better power quality to loads during short duration faults like voltage sags in the electrical system. Then time shift renewable energy is also possible with the help of these storage devices. Actually, power output from renewable energy sources depends on environmental conditions. It won't produce according to the demand from consumers. So, storage devices are used to store energy when the output is high from renewable energy sources and supply to the load when it demands. So that's all about the applications of storage devices.